Okay, so in this equation up here, we have aluminum, like elemental aluminum, and it's being combined with elemental oxygen, all right? And the process is going to create this new product. And we should be able to name this product. We should be able to name each of these components because we've done that work in nomenclature. So Al2O3 would be aluminum oxide. All right, aluminum is a simple ion. It's not complex, so it would not require a Roman numeral to be placed in front of it. And when you oxidize aluminum, it kind of looks like that. All right. Notice that well, I don't know what happened there. Oh, yeah. That on the front side of a reaction, typically on the left, there's going to be the reactants in most cases. And the arrow then is going to yield to the product. So what's produced in the reaction. This is a very, very simple, simplistic idea, I know. But we also include in a proper chemical equation some letters, so some symbols. The letters are going to be telling us the physical states of the components, of the compounds that are in the reaction. And then also we have numbers, and these numbers are going to be stoichiometric coefficients. Stoichiometric coefficients. Okay, so since we talked a little bit about these letters representing the physical states of the compounds, we should go into a little bit of symbol terminology. All right, so S, L, and G, solid, liquid, and gas, very straightforward. AQ means aqueous, or that's dissolved in water. So if we take like a solid salt, like sodium chloride, so a simple ionic compound, all right, and we dump this into water. Water would be actually noted as a liquid. Pure solvents get the L after their chemical formula if they are pure solvent. But when we put salt water into solution, when it dissolves, we would note it as being aqueous, or AQ. In fact, a lot of the stuff that we work with in chemistry would be in aqueous state, dissolved, because it helps it be more mobile, right? If something is dissolved, instead of like big, huge salt crystals, they are now like individual units of NaCl all moving around in that fluid of water, that solvent of water. So a little bit more information on what we mean by aqueous. If something is said to be soluble or in solution, that also indicates that a substance is usually dissolved in water or will dissolve in water. Anytime you come across an acid, it's going to be aqueous. Obviously, the arrow means that we're simply yielding or producing a product. The triangle or delta is going to mean that energy or heat has been added to the reaction. So to represent that, we might say, all right, well, if we take magnesium carbonate and we decompose it into magnesium oxide and carbon dioxide, well, how does that happen? That happens through the addition of heat energy. We have to heat this thing up to decompose it. If we actually have to run the reaction at a certain temperature, then we would provide that information along with the yield sign. So maybe just knowing that to add heat to it is good enough. Maybe there's a specific temperature at which the decomposition might happen, or that the synthesis reaction or replacement reaction might happen. So that can be noted as well. If it requires a catalyst to help the process happen, then we would include that as you would expect right above the yield sign. Right. For this final one, we have looks like ethene is going to be combined with hydrogen gas. So we have a hydrocarbon with hydrogen gas and making it into ethane. And platinum is a catalyst that will help that happen. The platinum, a catalyst just like an enzyme, is not affected or changed by the reaction. It simply kind of helps them get there. It is making note of whether a precipitate shows up or not. Okay, so a precipitate is going to be where we, in the product area, we have a solid that forms, or a product that is insoluble in the solvent that the reaction is occurring. Right, so we're going to take a couple ideas, a couple compounds here. Sodium carbonate is aqueous in water. So is calcium nitrate. Right, so we mark that they are aqueous, that they dissolve in water. right? And if we consider what could be the possible products here, well, you almost kind of know if something was going to happen, what that something might be, right? I mean, it does not make sense for the sodium to be with the calcium. Why? Why would it not make sense that if a product will be made, it won't be one where we have sodium, calcium? Yeah. Yeah, because they're both metals. They're both cations, right? They're both positive charged. So why would they want to hang out with light charged things? It's not gonna benefit them in any way to complete their electron valence. So we know that would not happen. For the same reason, but the opposite charge, that the carbonate and the nitrate would not hang out together, right? In a product, right? So you can kind of see, like, if anything's going to happen, it's going to be like the old switcheroo. It's going to be where sodium's going to be hanging out with nitrate and calcium hangs out with carbonate. They're going to trade partners. And so if that does in fact happen, then we would see a process occur. If it would not make sense for us to say that sodium carbonate becomes more sodium carbonate because we already have that. So we can kind of look at what we have and decide, like, what is going to be rearranged with what, and then we can also use those charges then to help us build in the proper product formula, right? We know that carbonate is a 2 negative charged polyatomic anion, and calcium is a 2 plus, so 1 to 1 will work for its compound. And then for sodium nitrate, sodium is a 1 plus charge, nitrate is a 1 minus, so again, a 1 to 1 setup there. Now we have to make sure that mass is conserved, so if we check left and right, we notice that we need actually 2 sodiums and 2 nitrates to balance the 2 sodiums and the 2 nitrates that are found as reactants. We'll get into balancing equations in short order, but for today we just want to be able to go from the written word of an equation to the proper chemical formulas of that equation and noting the proper state of matter. All right, so if we start with aqueous stuff and we end up with a solid in our solution or in our container, we should start to see like little clumpy, globby things showing up as this reaction happens, right? And that is the solid precipitating out of solution as they collide and find one another. And so we would note that is the precipitate. Right? So sodium carbonate dissolved in solution is a clear solution. Calcium nitrate dissolved in solution is a clear solution. But when we actually combine these two together, it'll become quite a cloudy product or result. Right? The cloudiness of it is going to be the calcium carbonate. The sodium nitrate then still remains in solution. So what we could do is we could filter this because now we have a solid. And with the proper filter size, we could run this through the filter. The calcium carbonate would be trapped in the filter. The water with the dissolved sodium nitrate would be found in the beaker below. Just keep in mind that in a reaction, that these atoms are going to get rearranged. It's very much the same way like you might play with Lego blocks or building blocks of any kind. You can start with your reactant, but then at the end, you have the same number of blocks to play with. They're just arranged in a different order. The other idea is that mass, energy, and even charge is conserved from beginning to end. Right. A balanced equation is going to be one in which the numbers of each element of every reactant is equal to the number of elements found with the products. If we don't balance them, then the equation really does nothing more than tell us like what we're making from what reactants. Like that's about all you can do with it. It does not give you anything in terms of the relationship of quantity, being able to predict how much you have to how much you will make, or if you were to run a lab and measure something being produced, you could use the balanced chemical equation to backtrack to what you may have started with. We can also use the balanced chemical equation to determine which reactant would run out first. And we would say that that reactant that does run out first would limit the reaction. Okay, so we have a plan really in place for trying to balance these chemical equations. The first thing is obviously write a word equation for the reaction. We've been doing that, right? We either were provided a word equation or in some examples that will come up in the near future, you're given like a story almost or an explanation of a reaction happening, and from that you need to parse out what's important to set up your reaction of the equation for the reaction. We need to write the correct formulas for all reactants and products, which we kind of practiced that yesterday. And remember that once you have the formula for the compound determined, you should never change the formula, the subscripts, while you're trying to balance. Okay, so once you have the proper formula in place, now the only thing you can really adjust for is like numbers of whole molecules, I suppose, of what you're going to be using. I don't really like the way that the reference text, as well as like if you do a little searching around the web, there are many people who would say that balancing chemical equations it's a little more than trial and error. I mean, there is a strategy to it. It is like a puzzle solving sort of approach to make sure left and right sides balance. Some equations are balanced right away. Right? As soon as you form the proper compounds, they're all balanced right away. With others, you actually do have to inspect, balance by inspection, to look at how many of one element is present on the left versus those on the right, and we'll walk through a method that will help you get to the final balanced equation as quickly as possible without wasting your time. But there are a few tips that we'll learn along the way. First, always try to handle the most complex or polyatomic ions first. Because if you change the number of them that you're using, it changes several elements all at one time. Okay, so you always try to handle the most complex or polyatomic ions first. All right, the second idea, evens and odds. If you have something that you have an odd number of, it's difficult to make. You can't make even numbers odd again, right? Like by multiplying them by some factor, some whole number factor. You just can't do that. So if you do end up with evens versus odds, then usually the strategy is to make the odds even, right? Because then you can work in comparable amounts. All right. So yeah, try to make everything all even if possible. And then you should always try to save oxygen, hydrogen, and elements that you find all by themselves for last. Because if you change like the coefficient in front of them, you only change that one element. Like if it's just silver, so Ag. If you need 25 atoms of Ag to make the equation balance, so be it. When you make that change, you only affect that one element. Versus when you change a number in front of a complex or polyatomic ion, if you need more nitrate, then for every time you increase the number, you're adding another nitrogen atom plus 3 more oxygens for every time you increase the number. So this is just 3 tips that really kind of help you avoid getting lost or avoid spending more time balancing than what you need. Right, so if you want to write the word equation for the reaction of methane gas with oxygen gas to form carbon dioxide and water, I guess a side note, this is a combustion reaction because we're taking a hydrocarbon fuel source and we're combining with oxygen and we're producing carbon dioxide and water. Every single combustion reaction, provided it's complete combustion, will run in this format. A fuel source plus oxygen yielding carbon dioxide and water. So if you want to write the equation for this, then we know that methane and oxygen are going to be our reactants, right? And then carbon dioxide and water are going to be our products. And it's to form or to yield or makes or whatever. There's usually a statement in that phrase that denotes the difference between the reactants and the products. Sometimes they try to get tricky on you and they'll say like, carbon dioxide and water are formed from, And so they'll give you the end products first, and then they'll circle back in their statement and tell you like what was used to make them. Right, so you have to read carefully and make sure that the arrow points to in the right direction as far as like what are the reactants and what are the products. Methane. If we try to dig into our organic chemistry knowledge, if we remember anything from maybe biology or AP Bio or biochemistry, methane means one carbon, and the ane means it's saturated with hydrogens all the way around. So that'd be CH4 for methane. All right. Oxygen. What would we use here? It's going to be O2, yeah. Yeah, elemental oxygen is always going to, oxygen gas, elemental oxygen, whatever, will always be diatomic. It's always O2, all right? So there we go, O2. And then carbon dioxide, we've already talked about that today, that's CO2. And water, we've already talked about that today as well, H2O. So pretty simple, pretty straightforward to go from, again, a written statement to a word equation to the chemical formula equation of the process. Now, of course, looking at this by quick inspection, we can try to bring this to balance. It is not balanced. There are 4 hydrogens on the left and only 2 hydrogens on the right. Oxygens, we have 2 on the left and 3 on the right. And hydrogen, we did hydrogen already. Carbons are balanced in this case. Right, so as far as an approach to balance this one's not too difficult for us, I think, by inspection to determine what we need to do here. But remember, one thing that we mentioned is work with the most complex thing first. Methane would be probably the more complex of them all here. But I'm not sure we don't really need to go working with it directly, because we have 4 hydrogens over on the left, but only 2 on the right. So maybe we want to focus our attention on the water. We know, if we recall from our tips, that we need to try to make odds even, and we have an odd number of oxygens on the right-hand side of the equation. So if we do fix the number of hydrogens with making it 2 waters instead of just 1, that will bring us to 4 hydrogens on the right-hand side, which is balanced. So hydrogens would be balanced if we did that. And then it also mentioned in our tips that to save single elements for last, like hydrogen, oxygen, and single elements like O2 for the very last. And really, what we would end up with is 4 oxygens total on the right-hand side, and we can easily fix that by using 2 molecules of oxygen on the left. All right, so if again, that's a quick use of those tips and tricks to try and make sure you bring things to balance very quickly. A solid iron reacting with oxygen, and it's going to yield iron 3 oxide. So we're rusting some iron. We have a piece of iron is laying out there in a scrap air or something, and oxygen in the atmosphere is reacting with it. All right, so what we want to do is move this from the word equation into the formula equation. Well, solid iron is just elemental iron, so it's just Fe. Elemental oxygen is just O2, so we may make note of that. And it's going to produce or yield solid iron 3 oxide. What's the formula for iron 3 oxide? Fe2O3, because we have iron 3, which is 3 plus. We have oxide, which is a 2 negative. And so we can use crisscross method. We can use making sure that the charges balance. So we need 6 plus and 6 negative total, and Fe2O3 makes that work, or allows that to work. All right, now we can also represent what we have here with images. I mean, we can make this as simple as we want and pretend that, say, if all coefficients are 1. If we don't put anything in these blanks, then we make the assumption that we need 1 of each of them that are there. All right, and we can represent iron iron with a star. Right, oxygen is 2 atoms of oxygen, so we could put a couple circles linked together to represent oxygen, and that would mean that Fe2O3 would have a couple stars and 3 circles all put together. Right, and if we consider that, is this balanced? If we ask ourselves, is this equation balanced? Well, right away, from the images or from the numbers, if we do the arithmetic, they're not. Right? We don't have the same numbers of things on left and right hand side. Right? We're short a number of iron on the left versus the right. We're short number of oxygen atoms being used left and right. All right, so we could fix this by changing the subscripts. We could break that rule. We could break that law and say, you know what, forget it. We're just going to get this balanced by changing the subscripts, right? And then we could represent that again with images or symbols, and we now have a balanced chemical equation. The problem is O3 is not oxygen; it's ozone. It doesn't behave the same way chemically. So remember that changing a subscript will change the substance. If we want to balance, we only want to modify the coefficients. So right now we're not going to worry about superscripted things. If we were to get as far as oxidation reduction things, then we would start considering charges, which would be shown in superscripted form. But for right now, they're not going to worry. We're not going to worry about those as far as balancing equations. So really, to balance this properly, we simply start with the most complicated substance first and leave the simplest substance last. And it's very simple for us to go take care of oxygen first, to balance it with the Fe2O3, make the odds even. That would allow us to make it match on the left-hand side as well with 6 oxygens on either side of our equation. And then finally, we can clean up with the element that's all by itself, noting that we need 4 of these guys to make things work. And I broke the web.